Alright, let's do some quick practice problems. It says qualitative analysis shows that a compound contains 32.28% sodium, 22.65% sulfur, and 44.99% oxygen. Find the empirical formula of this compound. Alright, so we have to keep in mind that the empirical formula is the smallest whole number ratio of moles. So we need to figure out how many moles of each of these elements we have and then compare them to figure out what the ratio between them is. Alright, so first things first, I'm going to pull in tip number 1 here where you assume 100 grams of this compound. And I think you're going to find out really quickly here why assuming 100 grams is so important. If we start with our sodium, well, what is 32.28% of 100 grams? 32.28 grams. So we've got 32.28 grams of sodium in this 100 gram sample that we assumed. Next, it says 22.65% sulfur, which means that 22.65 grams of sulfur in this 100 grams. And then lastly, we've got 44.99% oxygen, which means of that 100 grams, 44.99 of it is going to be oxygen. Okay, again, empirical formula is the smallest whole number ratio of moles, so we just need to figure out how many moles each of these mass values is equivalent to, which means that we simply need to determine, using the molar mass. And so again, if you wonder where these numbers are coming from, we have to go to our periodic table of the elements. Sodium is located here, sulfur, and oxygen. So it's simply a matter of plugging those values into our setup here. 1 mole of sodium is 22.990 grams. 1 mole of sulfur is 32.066 grams, and 1 mole of oxygen is 15.999 grams. Again, all of those values coming from the molar masses on the periodic table. When I put this into my calculator, and I'm only going to do it for sodium here so you can see how it's done, we get 32.28 times 1, enter, divided by 22.990, enter. We get 1.1404 moles. 0.404 moles of sodium. Again, you want to do the same thing with sulfur, and we get 0.7064 moles of sulfur. And when you do that with oxygen, we get 2.812 moles of oxygen. Now, the empirical formula is the ratio, or a comparison between these amounts in moles. And some of you will be able to look at these numbers of moles and already figure out what the ratio is because you're mathematical geniuses. In fact, it might be easier if we cut off some of these digits here. Basically, we're comparing 0.7 to 1.4 to 2.8. How do those things compare? If I were to set up a ratio, what would it look like? This one may be easy for you to see, but it might be difficult. And in some questions, it's going to be a little more difficult to determine what the ratio is. So all you need to do, if you are unable to see what the ratio is from the number of moles, the easiest thing to do is simply to take the number of moles of each element and divide them by the smallest number of moles, and that will give you the ratio between the elements every single time. When it's easy to see and when it's maybe a little more difficult to see, it'll still give you that ratio. And so if I divide each of them by the smallest number of moles, which in this case would be the 0.7064, this one is going to be, well, 1. Okay, but if we plug the rest of those into our calculator, you might be able to do the first one in your head. 1.404 divided by 0.7064, we get 1.98. So this one is going to be close enough. We're within 1/10 of a mole that we can say, oh, that's about a 1 to 2 relationship. And then if we do the same thing with oxygen, we find that we have 2.812 moles of oxygen. We compare that to the 0.7064 and we get 3.98. Again, we're close enough that we can say, oh, this is pretty much a ratio of 1 to 4. So we've determined our number of moles, we've compared them to give us our molar ratio. So how does sodium compare to sulfur compare to oxygen? And the ratio is 2 moles to 1 moles to 4 moles. Therefore, our formula, our empirical formula, our smallest whole number ratio is going to be Na2SO4, conveniently sodium sulfate. And again, I'm just going to box this in as my final answer here for the empirical formula of this compound. All right, now that we know what we're doing, let's pick up the pace a little bit. It says, analysis of a 10.10 gram sample of a compound known to contain only phosphorus and oxygen indicates a phosphorus content of 4.433 grams. What is the empirical formula of this compound? Okay, so this one's a little bit different, but it's the same idea. We're trying to figure out what's the smallest whole number ratio of moles, aka the empirical formula. Note though, we're given this time the mass of 10.150 grams. We're not given a percent composition here. And we know that 4.433 grams of that 10.150 gram sample must be phosphorus. Okay, well then how much oxygen do we have? I have no idea, it doesn't tell me in the problem. Let's think about this. We know that we've got a 10.150 gram sample. We know that 4.433 grams of it is phosphorus, and this compound is only phosphorus and oxygen. Therefore, let me bust out my calculator. 10.150 minus 4.433. That means that the rest of this thing must be made up of 5.717 grams of oxygen. And once we know the masses in grams, it's just a quick conversion to number of moles. And then once we know number of moles, we just compare to get our empirical formula. Moles, oxygen. So here it's a ratio. For 1 mole, there's 30.974 grams of phosphorus. And here in 1 mole, it's 15.999 grams of oxygen. If we plug this into our calculator here, 4.433 times 1 divided by 30.974, 0.1431 moles of phosphorus. We do that same thing with oxygen, and we get 0.3573 moles of oxygen. Now again, this one might be a little trickier to tell what the ratio is or a comparison between the two. I know it's not 1 to 1. I know it's not 1 to 2. That would be 0.14 to 0.28. But I know that this also got to be less than 1 to 3. Again, if you're mathematically inclined, you might be able to tell what this ratio is right away. But if you don't, and if you're confused, and you're like, oh my god, my life is over, fear not. You always just divide by the smallest number of moles. And if we do that, here we get 1, and when we do that with oxygen, I'm going to use my calculator. We've got 0.3573 divided by 0.1431 equals, oh man, 2.5. So this means that my empirical formula is P O 2.5? What? Okay, we can't write empirical formulas that have decimals as the subscripts. Again, empirical formulas are the smallest whole number molar ratios. And I can't just round this to 3 because it's not close enough. Remember, it's not within that 1/10 of a mole. And so, what we do is we think to ourselves, what can I multiply each of these numbers by? It's going to be the same number that will make both of them whole numbers. Well, I know the fractional form of 0.5 is 1/2. 1/2. The fraction, the denominator in the fraction, will tell you what to multiply each of them by. So if I multiply each of these by 2, I'm going to get a whole number. So this one times 2 and this one times 2 means that the actual smallest whole number ratio isn't 1 to 2.5. No, it's 2 to 5. So my empirical formula here for this compound that consists of just phosphorus and oxygen is P2O5. Boom.